Today we are going to talk about the relationship between the equilibrium constant and the delta G of a reaction at standard conditions. The problem states, use the free energies of formation listed in the table to calculate the equilibrium constant for the reaction at 298 K. So I went ahead and wrote the reaction that's given to us, and then the table is to your right. So notice that N2O4, the gas phase, has a 99.8 kilojoule per mole delta G, and then NO2 gas has a delta G of 51.3 kilojoules per mole. The first thing we have to do for this problem is calculate the delta G of reaction at standard conditions. And the equation for this is the sum of the moles of products times the delta G of formation for the products minus the sum of the moles of reactants times the delta G of formation for the reactants. So we have to go ahead and plug in our values for this. But we also have to take note of the coefficient right here. So when we write our equation, it's going to be 51.3 kilojoules per mole times 2, which came from the coefficient from the NO2 gas, minus 99.8 kilojoules per mole. And just so you understand that we still have to apply the moles to this, we're just going to put a 1 in front of this, even though it's going to be the same number. So once you calculate that, the answer is 2.8 kilojoules for your delta G at standard conditions, sorry. So we've already found the delta G of the reaction at standard conditions, which is 2.8 kilojoules. So then we have to plug that into the relationship delta G at standard conditions equals negative RT ln K. The R stands for the gas constant, which is 8.314 joules per mole times K. The T stands for the temperature, which because our gas constant has Kelvin as one of its units, that means our temperature has to be in Kelvin. But if you look back at the problem, the temperature that's given to us is 298 K. So it's already in K, so we don't have to do anything to that but plug it in. So 298 K. Now we're trying to calculate the equilibrium constant, which is K. So all we have to do is solve for K because we have all of our constants and numbers that we need for the equation. You also need to notice that our gas constant is written in joules. So in order for us to use this gas constant, we have to convert our kilojoules of delta G reaction at standard conditions to joules. So all we have to do is multiply by 1,000. And that gives us 2.8 times 10 to the 3 joules. So once we have this, all we have to do is plug it into our equation. So we have 2.8 times 10 to the 3 joules equals negative 8.314 joules per mole times K times 298 K times ln K. Now what we want to do is separate the ln K from the rest of the numbers. So what we have to do is divide both sides by the 8.314 times the 298. So it's going to be negative, so we have 8.314 joules over mole times K times 298k. Now once we've got that value, which go ahead and calculate it with me so you can follow along, we get ln k equals negative 1.13. Now we can't leave it like this because we want k by itself. So in order to get k by itself, we raise the entire equation to the e. And the reason why we do that is because e is a function of the natural log. So we can use this to convert. So k equals e to the negative 1.13. And once we've calculated that, k equals 0.32.